Okay. All right. So, hello everybody. Good morning and welcome to lecture 31. Right. So, in the last class, we talked about Faraday's law. Right? Faraday's law is the statement that if you have a changing magnetic flux or changing magnetic field, it generates an EMF. Right? An electromotive force. It generates an electric field. And how do you describe the action of Faraday's law? You say that if there is an electric field that is changing in the perpendicular direction, a magnetic field that is changing in the perpendicular direction, that will create a circulating electric field in the plane which is parallel to that perpendicular direction. Right? Ampere's law says that if you have a current in the perpendicular direction, then that creates a magnetic field in the circulating magnetic field in the plane perpendicular to that current, right? So we have these laws, and now I have talked about the differential form of both the laws. I've talked about the integral form of the laws, and let's see, right? So, but because this language is new to many of you, I keep emphasizing again and again in many classes, right? I keep repeating so that it will filter in better, I think, I hope. So once again, how many Maxwell's equations do we have? 4. 2 of them are divergence, 2 of them are curl, right? Divergence of electric field is not 0. It's equal to the charge density, right? Charges create electric fields. Divergence of the magnetic field is 0. There are no isolated magnetic charges, right? Then, along with these equations, you have to remember the divergence theorem and Stokes theorem. The divergence theorem tells you that if you take the integral of this quantity over some volume, it's equal to the flux of that quantity over the surface of that volume. Since this divergence is 0, its integral will be 0. That means the flux will be 0. The integral of this divergence will be the integral of the charge density. The integral of the charge density is equal to the total charge. So the total charge is equal to the electric flux within any given region, right? Then we have the 2 curl equations. So if you have a current, it creates a magnetic field. But if you have a changing electric field, that will also create a magnetic field. This equation is due to Maxwell, right? And we'll talk about this equation today. Now, when you talk about curl, Stokes theorem is what matters. Stokes theorem, this is a vector quantity. I can calculate the flux of this vector quantity through any surface, right? So if I take the flux of this quantity through any closed surface, and just for reminder's sake, bring up that nice picture, right? So you can take any surface, you calculate the flux of this quantity through the surface. The flux of the curl of that vector field is equal to the line integral, the circulation of that vector field around the boundary of that surface. So if you have a closed surface without any holes, then what is the boundary of a closed surface? No, zero, right? A closed surface doesn't have any boundary. So if you take is it? If you take this quantity and calculate the flux of this quantity through any closed surface, what will you get? You will always get zero. Why? Because the integral of the flux of this quantity through any closed surface, right? So let's look at that again. I have the curl of B equal to mu naught J plus mu naught epsilon naught dE dt. I take some closed surface, which is a sphere, let's say, and I take I call this a vector field V. I calculate the flux of this vector field through the surface, right? According to Stokes' theorem, this flux can be written as a line integral of this quantity. So whenever you calculate the flux of some vector field, and that vector field happens to be equal to the curl of some other vector field, then this can be written as the curl of this B dot dl, the line integral of B dot dl around some closed curve. But for a closed surface, where, so C, what is this C? This is the boundary of the surface S. This, when I write dou of S, I mean, I'm talking about the boundary of something. If I take a disk, this is a disk, this is C, the circle, the boundary of the disk is equal to is like this. So this is the relation, C is the boundary of this disk. For a closed surface, the boundary of the surface is what? Zero. It doesn't have a boundary, right? So this means that for the closed surface, B dot dl is equal to zero, right? Because there is no curve. See, all the curves are zero, right? So this means that the integral of curl of B dot dA for some closed surface is zero, right? Now we can understand this by looking at the right hand side. So if you look at the right hand side, it has this, let's just look at the current term, mu times J. So when I take the integral of this B dot ds, when I take the flux of this quantity through the surface, right? That is the same as taking the flux of this quantity through the surface, right? So this is equal to integral of mu naught J, mu naught epsilon dE by dt through the surface, right? Now, let us take the electric field to be static, okay? Then what does this integral become? It just becomes integral of mu J dot dA, right? Now, what is J dot dA? You have some surface, right? And it's a closed surface, right? There is some current that passes through there is some wire that comes and it leaves the surface, right? So it comes in from here, it leaves from here, and inside, right, it does something within the volume, right? So this is carrying some current I, right? Or some current density, we can say, since we're talking about J, right? Now, if you ask, what is this quantity J dot dA, right? Well, here you will have some J in, and here at this point you will have some J out, right? Now, what will be this J in dot dA?
Current.
This will be the current going into this area element, right? And similarly, what will be J out dot dA? It will be the current coming out of this area element, right? So if you look at this integral, I can write this as sum of mu naught J in, right, minus J out. Why minus? So sorry, I should say minus J in plus J out, because flux is calculated with the assumption that the normal vector is outward pointing. So the normal vector here would be like this, dA. So the outward going, the current that is flowing out is positive. The current that is going in gives you a negative flux. Dot dA. So this integral becomes, through the surface, mu naught J in dot dA becomes minus di in, and this becomes plus di out. When I integrate over the whole surface, I simply get mu, the current going into the surface, and the current coming out of the surface, right? What is this going to be equal to?
I enclosed.
I have some closed surface. I have some wires carrying current that take some current into the surface and some current comes out of the surface. What is this going to be equal to?
Current that is flowing into the body, like into the surface.
It will be zero, right? This is the charge that is flowing into the surface. This is the charge that is flowing out of the surface. The total charge, can it be created or destroyed? No, right? So if I take any surface, any closed surface, it has to be closed. That's the most important thing. If it's not closed, then there is a hole. And through that hole, you can put in extra charges, right? Or remove charges. But if there are no holes, then whatever charge goes into some closed region has to be equal to whatever charge comes out of that closed region, right? So you get zero here, right? So this quantity is zero for any closed surface, right? And which agrees with the fact that curl of B dot dA, right, is equal to B dot dL, which is zero. Why zero? Because the boundary is zero, right? Okay. Now, so this is simply saying that charge is conserved, right? This equation, if I integrate this, if I take the flux of this quantity through any closed surface, I'll get zero. So if I take the flux of this quantity through any closed surface, I should also get zero, right? So if I did not know, let's say that I did not know about this equation, right? But I knew that so this equation is what do we call it? We call it M4, the fourth Maxwell equation. We did not know about M4, right? But we know that currents generate somebody has done the experiment in the lab, they find that the current generates a magnetic field. Guys, I asked you all to please turn your videos on. A couple of you have turned your videos on, but everybody else has turned them off. Please turn your videos on. Thank you. So we know that currents generate magnetic fields, right? Okay. But we don't know the exact equation. We don't know this M4, right? So what we can do is we can work backwards. I know that if I take the current, the flux of the current through any closed surface, this is going to be 0, right? So this has to be related to the magnetic field in some way, right? What should be the relation? Can J be proportional to B? Well, maybe, right? But we know that the magnetic field is not created parallel to the current. So this is not true, right? So if you say that J is proportional to curl of B, right? Then what is the integral of curl of B, the flux of curl of B through the surface? Where this is a closed surface.
0, 0.
This is equal to B dot dl by Stokes theorem, but this is equal to 0. So that tells me that J should be proportional to the curl of the magnetic. So from conservation of charge, I can derive this equation. I can guess what this equation should be, right? From conservation of electric charge, and from, of course, from knowledge of some empirical knowledge, right? Empirical knowledge means right, something that is gained via experience or via experience or via experiments, right? That's called empirical knowledge. Okay. But now we have to look at another example. So this equation is not complete. Why is this equation not complete? Okay. So let's look at what happens. Let's say that I have a battery and I connect it to, in a circuit, I connect it to a parallel plate, two parallel plates like this, right? Now I can calculate the charge on each plate, right? So this will have some charge plus Q and this will have some charge minus Q. And I can put a switch over here. This is a switch, right? So what happens to the charge? Well, initially the switch is open, right? Charge is 0. Then I close the switch. What happens to the charges on the two plates? The charge starts increasing, right? They start getting charged up. And they reach some maximum value, right? What is the maximum value? The maximum value of this charge, Q max, is given by the capacitance of this parallel plate capacitor multiplied by the potential of the battery, right? Right? Okay. Now, what happens as these plates are charging up? The moment I put some charge on two plates, right? I have some charge plus Q and minus Q. That means that there will be an electric field between these two plates, right? Now, I can ask, how does this electric field change with time, right? So again, what do I have? I have that initially the plate is uncharged, so there is no electric field, right? So if I make a plot of the electric field on the same graph, the electric field is 0. Then what happens? The electric field will also follow a similar pattern, right? It will reach some maximum. When the plate is fully charged, it will reach a maximum and it will stay at that maximum, right? Is this fine? So that means there will be some electric field here. And while this electric field is charging, what is the time derivative? It's not 0, right? The electric field is changing with time, right? So I have this circuit now. I have two plates, positively charged, negatively charged, and I have a switch. I have closed the switch. When I close the switch, the plates, they start to charge. Right? And they start to charge, so that means that there is some current that is flowing in the circuit, right? And I can make a plot of the current also, by the way. If I want to make a plot of the current, what does the current look like? The current also looks like this. It is 0 initially. Then I close the circuit. When you close the circuit, the current is at some maximum value. Okay. So maybe I'll take this and I'll put it here. So there's no, otherwise there's too much information in one place. So what happens? The current reaches, it starts at some maximum value, and then then the current starts decreasing, right? As the plates charge up more and more, the current slowly decreases until it goes to 0, right? Now, if there is current in this circuit, I'll make this black. If there is current in the circuit, then there is going to be a magnetic field that is generated due to that circuit, right? So there will be a magnetic field that is generated. Like this. Right? So there is a magnetic field in the circuit. Now, let us ask what happens at this charge plate, okay, at the charge plate, at that boundary. So we'll look at this boundary more closely. So this is my charge plate, positively charged plate Q. Now, as my magnetic fields are, initially, right, what happens is I close the switch, the magnetic field, there is a magnetic field, right, whatever it is. And there is some magnetic field. If I look at the other side of the plate, here also there is a magnetic field, right, due to the current. Right? Now, what happens in between the plates? In between the plates, is the magnetic field equal to 0? Right? Because I don't have any current that is flowing in between the plates. I don't have any charges that are moving between the plates. Right? I have an electric field that is increasing, but there is no physical movement of charge from one plate to another plate, right? There is no current, right? So you would say that I is equal to 0, right? I is equal to 0. So does this imply that the magnetic field is 0?
Yes, sir.
No, there is why is that? So we can actually work out, we can ask what happens to the magnetic field near the surface of some metal, okay? So you have a conductor. This is our conductor. This is our positively charged sheet. There is a wire that is coming in, which is carrying current into this conductor. Now, there is a magnetic field here, right? So I'll draw it like this. Now, as you reach the conductor from the left-hand side, what is the direction of this magnetic field? It lies in the plane, right? It lies in the plane of this. The magnetic field lies in the plane of this sheet of charge, right? So one can show from this divergence equation. So if we look at this equation, remember that we have this equation, right? Maxwell's equation. It says that divergence of B is equal to 0. When I look at the integral version, it tells me that the flux of the magnetic field through some surface is 0, right? So if I have some surface like this, and let's say that I have some magnetic field over here. Okay, 1 second. Let me just collect my thoughts one. Right. So let me show you what I'm trying to tell you by sharing this slide from Griffiths. Okay. So what happens with the magnetic field is that if you look at the flux of the magnetic field through any surface, it is 0, right? All right. So now this is my surface K. Now I make a box. I make a box such that the surface is going through the center of that box, right? Now there will be some magnetic field above the surface and some magnetic field below the surface, right? The flux of the magnetic field through the surface will be equal to the above component times the area minus the below component times the area, the perpendicular component above minus the perpendicular component below, right? So this quantity on the is equal to 0 on the right hand side. So this on the left is equal to the transverse component of B above the sheet minus the transverse component of B below the sheet. But this is equal to 0 because there are no magnetic charges. So that means that the transverse component of B above and below has to be equal to 0, right? What about the parallel component? We are interested in the parallel component because, like I said, current creates a like so this field is parallel to the sheet. So to do this, instead of looking at this flux, we should look at a closed loop like this. Okay, so let me again, I'll draw this diagram. So take some closed I have some closed loop. It's not showing up very quickly. All right. And I calculate, ask what is the magnetic field around this closed loop. Okay. So I calculate integral B dot dl. Right. Now integral B dot dl. So you have to imagine that this loop is like this. I have a closed loop like this, right? And my surface, this is my surface. So if I look at it edge on, this is the surface, right? So the loop goes through the surface and on the other side, like this, right? Now B dot dl from Ampere's law is equal to mu enclosed. What is mu enclosed? Well, that means there should be some current that is flowing through this loop, right? Some current should be flowing through this loop. Otherwise, this will be zero, right? Now, if you look at this sheet, on this sheet, are there any currents flowing on this sheet? There are no currents, right? I is equal to 0. Because we are making the assumption that, so if you were to view this picture in very slow motion, right? That means as each point charge comes into the sheet, it will take some time for the charge to distribute over the sheet, right? But we are working with the assumption that that process happens very fast. Right? So there's no current on the sheet itself. The total charge on the sheet keeps increasing, but there is no current on the sheet. Right? So if there is no current, if this is 0, then B dot dl is 0. Right? Now, here I have this B. This B is over here. And if I make my loop like this, this is my loop, then the integral of B along this loop has to be 0. Now, what is the component of the magnetic field in this direction? This is 0, right? There is no magnetic field along the wire. There is no magnetic field along the wire, right? There is a magnetic field along this edge. For this integral to be 0, there has to be a magnetic field along this edge also, and it has to point in the same direction. Right? So you can think of it like this. The magnetic field here is B. The magnetic field here also has to be equal to B. I'll call this the parallel component. And here, this is the perpendicular component. This is 0. This is the component of the magnetic field perpendicular to the surface. It is 0. Right? So if integral B dot dl is 0, that means that B parallel above the sheet has to be equal to B parallel below the sheet. Okay. What this means is that I have this magnetic here. Since this magnetic field, so basically it means that the magnetic field is continuous across the sheet. So as I go from this point to this point, as I go from the wire to the empty region, the magnetic field has to be continuous. So if the magnetic field is continuous, that means there has to be a magnetic field here also. Okay. but there is no current here, right? There is no physical flow of charge. So how can I write down curl of B, right? Because Ampere's law tells me, so I have that magnetic field parallel to the sheet is continuous as I move from one side of the sheet to the other, right? From one side of the sheet to the other side, right? But on one side, I have curl of B is equal to mu naught J, and J is not equal to 0, right? And on the other side, I have curl of B is equal to mu naught J, but J is equal to 0, right? Does this imply that B is equal to 0? No, because I know that the magnetic field is continuous as I move from one side to the other, right? So if I don't want a contradiction, I have to put an extra term over here, mu naught J plus extra term. This extra term will depend on the electric field, right? And it looks like this. So now as I go from one side of the, if this is, let me call this region 1 and region 2, and let's say region 3. So this is plus Q, minus Q. Here I have some current, I. So this is region 1, and this is the current, not to be confused with region 1, right? And so I'll put an I naught. But here in region 2, there is no I naught. Sorry, I naught is equal to 0, right? Here it's not 0, here it's not 0. So in region 1 and 3, curl of B is equal to mu naught J. In region 1 and in region 3. And in region 2, what happens? Curl of B dou E by dou T in region 2, right? Now, let us go back to this charging procedure. So what happens once the plates become completely charged? What happens to the current in the circuit? Current becomes 0, right? Once current becomes 0, what happens to the electric field? Does the electric field go to 0? No, the electric field is still there, right? But it's not changing in time, right? The electric field has reached a maximum value, it is not changing. So once the current reaches 0, the magnetic field around the wire disappears because there is no current here. And since the magnetic field around the wire disappears, the magnetic field between the sheets should also be zero by continuity. Right? So the magnetic field cannot depend on the electric field, right? Because so it has to depend on the time derivative of the electric field. When there is a change in electric field, there is a magnetic field. And this expression is known as Maxwell's correction. He realized that even when there are no currents, you can have a magnetic field only by changing the electric field. So this is like the opposite. This is like the dual of Faraday's law, right? What does Faraday's law tell us? Faraday's law says that if I have a changing magnetic flux, it creates a EMF, right? It creates a E dot dl term, line integral of E. What is this Maxwell's law telling us? Maxwell's correction term, it tells us that when we have a changing electric flux, it creates a net magnetic field. And that magnetic field has a circulation. So if I take the line integral of the magnetic field, I get non-zero value, right? So changing electric flux creates a magnetic field. Changing magnetic flux creates an electric field. And this is the basis of electromagnetic waves. Okay. So let me write down Maxwell's third and fourth equations, one or all of them. M1, divergence of E is equal to rho by epsilon naught. M2, divergence of B is 0. M3 is, what was the label that I used? Right. Curl of E is equal to minus dB by dt. This is also known as Faraday. This is also known as Gauss. And then M4, curl of B is equal to mu naught J plus mu naught epsilon naught dE dt. This is known as Ampere. This part is due to Maxwell. Okay. Now, 5-10 minutes maybe. I just want to introduce the notion of electromagnetic waves. Is that okay with others? Okay. So now we look in a vacuum. In a vacuum means there are no sources. What happens in a source-free region? The charge density is 0 and the current density is 0. Okay. So what happens to Maxwell's equations? In a vacuum, you get divergence of E is 0, divergence of B is 0, right? Because there is no charge density. Then you have curl of E is equal to minus dB dt. And curl of B is equal to mu naught epsilon naught dE dt. Being a little bit slow. I'm trying to turn my Wi-Fi on. Okay, so now what happens is that because of this Maxwell term, we get electromagnetic radiation. We get electromagnetic waves. Okay, how do we get electromagnetic waves? I have in this expression, I have curl of E is equal to minus dB by dt. Right? Now what I do is I take the curl of this equation. I take the curl of the left hand side. What that gives me is curl of E. And on the right side, I take the curl of dB dt. Right? Now, on the left side, I have this curl of dB dt. So I will get terms like this, right? I will get d by dy dbx by dt, right? These will be the sort of terms I will get, right? So I can write this as dou square bx, dou y dt, right? But I can switch the order of these partial derivatives, right? Partial derivatives commute. So if I have a function, I take its partial derivative with respect to x and y, or with respect to y and x. I get the same, I have to get the same answer. So that means that I can write this expression and I can take this equation and put the curl in the inside of the derivative of the time derivative. You should sit down and work this out component by component and make sure that it is indeed what I'm saying is correct. Okay. So then what happens is my equation becomes curl of E is equal to minus d by dt curl of P. Now curl of B is equal to this expression in terms of E. So I can put that in here. I get minus mu naught epsilon naught.
Sir, why an extra minus sign over there?
Where?
Curl of E.
This minus comes from here, right? I have a minus sign in this.
Got it, sir. Got it.
Right. So now I have an expression. I have E on the right. I have E. I have removed the magnetic field, right? So curl of E is equal to minus mu naught epsilon naught. Okay. So now I will leave you with some exercises. Okay. So this is a vector identity. Now in this vector identity, I set A is equal to B. If I set A is equal to B, what do I get? I get A cross C becomes A times A dot C minus A square times C, right? Because B is equal to A, so A dot B is equal to A square. So work out both of these expressions. And then in tomorrow's class, I will show you how you get electromagnetic waves from this equation. Okay. So you have to, there are a couple of exercises for you to do. Of course, I'm not going to sit and correct these exercises. But if you want to follow the material, then it would be helpful.
Sir, just can you tell why the closed integral b bar dot dA bar is 0? That thing I didn't understand. Like only for the closed surface or for anything?
Which integral?
Closed integral b
Which
bar dot
integral?
d. Closed integral b bar dot dA bar.
This integral.
Yes, sir. Is it for only the closed boundaries or for anything?
Yeah, it's true only for a closed surface, right?
Yes, sir. Then
This is also true only for a closed surface.
sir, but the sheet is okay. Done. Yes, sir. Nothing.
Because if I want to go from here, this divergence to this expression, I have to use the divergence theorem, right?
Yes, sir.
Divergence theorem applies to a closed surface only.
Closed surface.
If you have a surface with holes, the divergence theorem will not apply.
Got it. Thank you.
Okay. But when I talk about these quantities, here the surface is the blue surface is not closed or any open. It doesn't matter. I'm just taking some portion of the surface and I'm putting a loop which intersects the surface like this. That's all I'm doing. So I can do that with any surface, whether that surface is open or closed. So another thing that you should work out. Let me give you another exercise, which is about this equation. That's another exercise for this circuit with a capacitor, right? We have this relationship, right? I is equal to V by R, right? And what is I? I is equal to dq dt, right? So, and what across the two plates, right? Now, what is the potential across the two plates? If I have two plates like this, plus Q and minus Q, I have an electric field going between them. I can use my equations for the electric field for an infinite sheet of charge, right? Remember what that was? Electric field is sigma by 2 epsilon naught. In this case, here I will get electric field is equal to sigma by epsilon naught because of there are two sheets. So what is the potential difference between these 2 points, between point A and point B?
Cos integral E bar dot dA bar.
Integral of E dot dl from point A to point B, which is just equal to sigma by epsilon naught times this, whatever this width is, okay, L. And what is sigma? Sigma is the charge density, so I can write that as Q by A, right? Q by A is the area of the sheet, right? So this is actually just a statement that V is equal to, so you have Q is equal to CV, right? So V is equal to Q by C. This is just equal to Q by C. Minus V is equal to, well, so I have one equation which tells me that I is equal to V by R, which is equal to dQ by dt. And what is V? V is equal to Q by C. So I can write this as Q by RC, right? So I get this equation, dQ by dt is equal to Q by RC. Okay. And there has to be a minus sign here, I think. Yes. Minus sign. Yeah. There will be a, no, this is fine, this is positive sign. So the exercise is as follows. Solve this equation for Q as a function of time. Okay. So this is very easy to do, right? Solve this equation for Q as a function of time and make a plot of Qt versus T. Okay. And with the Qt is equal to 0, at T is equal to 0. All right. So unless I think I'm doing it correctly. So what you should get is that you should get this curve, this orange curve, which shows that Q increases and then saturates. Okay. So I'll stop here. So I have given you a bunch of exercises. Yeah, who are the people who are disliking my video? Huh? And my class is not even complete and people are disliking my video. Anyways. So yeah, questions. Any questions?